Hi, I'm Debbie Wheeler. I teach at Sayre School here in Lexington. Sarah Nolen is also with me. I'm going to be presenting energy flow and power, including some of the math components that you'll need to know related to that unit. And Sarah will be presenting the aquatic and terrestrial pollution unit. Couple of basics. So, I don't know why it does not want to advance. There we go. There are a variety of people that may be watching, viewing this presentation. Keep in mind, AP is College Board trademarked course. Mr. Lou Acampara is our Senior Content Director for Science at AdvKY. His email information is available for you as well. If you would stay muted unless you're asking questions or talking, I'd love to have some talking, and hopefully you'll communicate either via chat or your mic, but just to make sure it's a good presentation for everybody involved. Try and keep your mic off unless you're talking. And videos are turned off upon entry. If you leave your video off, you'll likely have some better bandwidth, so that might be a good idea. And please use the chat often. I'd like for this to be as interactive as possible, and questions are always welcome. Our review sessions, this one's being recorded. The past review sessions have also been recorded, and those are available at the bit.ly AdvKY link you can see on your screen now. Any handouts, I don't have handouts for my session, but there are handouts for other sessions that you can also access there. Okay, I'm going to transition and start my presentation on energy flow and power. You'll give me just a minute. Apologize for the messiness of my screen as I do that. Okay. In this unit on energy flow and power, I'm going to talk a little bit about traditional, energy flow in an ecosystem with producers and consumers and that sort of thing. But then I'm going to also touch on the energy unit, renewable, non-renewable energy, and talk about the calculations you'll need, and just tie into maybe some of the presentation that was done last week on energy flow as we look at it from a math perspective. Okay, so let's get going. So energy flow is going to involve obviously trophic levels. So in the chat, would you just throw in there some trophic levels to get your mind thinking about environmental science again? Primary consumers, I see. Any others you want to throw out there? Producers, yep, tertiary, secondary consumers, awesome. So this is a fairly straightforward question that was on an FRQ the College Board's given in the past. Identify a primary consumer. And again, please throw those in chat, or if you'd like to use your mic and speak up, you're welcome to do that as well. So identify a primary consumer in this drawing. Not seeing many responses, but I think you guys know, I may have said primary consumer, a primary producer. So maybe that was confusing because you can see it says identify a primary producer, but I may have said consumer. So seaweed and algae would both be good examples of a primary producer. Let's try the next one. Can you identify a tertiary consumer in this grouping? Identify a tertiary consumer.
Maybe it's just my screen, but I still see the slide of the content review sessions. Is anyone else seeing?
Yeah, I'm seeing that too.
So maybe that's why they're not hearing.
Okay, thank you. Then that may be part of my issue. Let me try again.
Okay.
Do another screen share, and maybe this one will work a little bit better? Certainly makes me feel better as to why I wasn't getting a response if you guys weren't able to see my screen. Thank you for your patience. How about now?
Yes,
Now we can see it. Yes.
So I bet we'll get some
Excellent.
answers now.
Excellent, thank you. Okay, so we talked a little bit about trophic levels. Now that you can see the screen, could you throw in the chat some examples of a primary consumer? And remember, primary consumers are going to be, or sorry, thank you for primary consumer. I said it again, producer, primary producers. Fish are a good example of a primary consumer. I did, definitely said consumer. Can you give me a producer? Yes, seaweed and algae, excellent. What about a tertiary consumer? So hopefully you can see the screen okay, tertiary consumer. And yes, herring gull. So the herring is eating the limpet, and the limpet's being, or sorry, the limpet's being eaten by the lobster. The lobster's being eaten by the seal. The seal would also be a tertiary. The herring will have to go from seaweed to sea snail to crab, and then our herring gull will be our tertiary consumer. Two organisms that compete for the same food source. Identify two organisms that compete for the same food source. And there are a lot of possibilities in this drawing of two organisms. So the fish and the sea snail are both competing for seaweed. That's a great example. You might also say the limpet and the sea urchin. Thank you. Yep, I see that in the chat now. They're both competing for algae. So these identify questions, you guys are responding exactly as would be expected. You don't have to necessarily put it in a complete sentence. You're simply identifying. When we hit some describe, that's going to be a little bit different. So in this image, you're given a table here, and it says, give us an example of an organism that would be affected if snakes were suddenly decreasing. And I think it takes a minute to look at this table. I would recommend that when you see this on the exam, that you, before you even read the question, kind of notice we've got consumers in this first column, shrews, hawks, grasshoppers, snakes, and spiders. And then across the top, it's got, the things that are being eaten. So can you just throw in chat just to make sure you understand how to read this? What do shrews eat out of those organisms? What do shrews eat? Grasshoppers, excellent. Okay, so based on the data they've given us in this table, if the snakes were suddenly gone or suddenly decreased, which of those, and I think I've already highlighted it for you, which of those would be affected? I may have to change screens, guys. I'm sorry. My laptop is.
Excuse me, Debbie.
Yes.
This is Tina here. Okay, so I have a student that's trying to get on. She's the one that's had the most trouble.
Yeah.
And oh, okay. Now she says, because she says it keeps telling her the meeting hasn't started. I told her turn off her computer, turn it back on. Now she says it's the old link for May the 1st. Okay, so I don't know how she's getting that.
Okay. Can you send her the newer link? There are 2 links.
Okay.
All the links are listed on the website, and it's easy to.
Okay, I'll try to send her that one that you all sent me.
Okay.
Okay, thank you. Sorry about that.
Absolutely. So back to our table, and I think I'm on the right slide now. If the number of snakes were suddenly to decrease, which of the following changes would most likely occur? And I did have this already highlighted, but we would have both an increase in the number of shrews as well as a decrease in the number of hawks. So because snakes are eating shrews and the hawks are going to be eating our snakes, then you can see how both of those would be associated. So I wanted to include a table as you think about energy flow, because that's one of the things that you'll also see on your exam in just a few weeks. Energy pyramids also give us information about primary productivity. Can you look at this graph, this diagram, and maybe you already know, what is the difference between gross primary productivity and net primary productivity? What is the difference between gross primary productivity and net primary productivity? And if you'd like, you can also talk about that like an equation. That's kind of the way I think of it. And gross is also, you know, if you get paychecks, you might think about your gross pay versus your net pay. And so my gross paycheck is maybe going to have all of the money that I would expect to make based on my hourly wage, and the net is going to be what I actually take home. And I'm not seeing some responses. You guys let me know if for some reason my screen isn't showing what I expect. But gross primary productivity minus respiration is going to give you net. And so producers are making sugars, but they're going to use some of those sugars for cell respiration. And then what's available to the rest of the food web is going to be the net primary productivity. So keeping that in mind, if we have a pine forest on a lava flow in Mount Fuji, and the net primary productivity is 175,000 kilocalories per meter squared per year, and the plant respiration is 115,000 kilocalories per meter squared per year, what is the total amount of energy that's transferred doing photosynthesis for this ecosystem? So having a pencil and paper handy is going to be good for this presentation. But if you would put in the chat, once you've had a moment to do the math, what is the total amount of energy transferred during photosynthesis? And I'm not hearing anybody. Hopefully you guys are hearing me okay. The best answer here is to add 175 and 115, and that would give us a total amount of energy transferred of 290,000 kilocalories. So remember, again, gross primary productivity is net plus respiration. Okay. Okay, what percent of energy is transferred from one trophic level to the next? Thanks, Olivia. What percent of energy is transferred from one trophic level to the next? So this is something you'll have to memorize. Yes, excellent, 10%. And so if producers contribute 100,000 calories, how many calories are going to be available to herbivores? Yes, 10,000 calories. So there are certain formulas that you want to make sure you memorize. And that 10% rule is one of the ones that you want to be able to use. Okay, here's another one. Algae in an aquatic food chain converts solar energy into 93,000 kilocalories of plant tissue. Which of the following values best represents the amount of energy available for secondary consumers in the food chain? So remember, we're talking about secondary consumers. A, nice. So we're just moving our decimal point over. So we've got 9,300 kilocalories would be available for primary. And then for our secondary, it would be 930. Well done. Okay. Let's talk a little bit about the laws of thermodynamics, because you may see those mentioned in equations. So whenever we think about energy flow, we should know the first law. Could you guys take a minute to type in, or if you'd like to say out loud, the first law of thermodynamics? Energy can change form, but it can't be created nor destroyed. Excellent. That is absolutely correct. We also want to keep in mind that in a closed system, the amount of energy remains constant, and that's still in line with the first law. What about the second law? Whoops. What about the second law of thermodynamics? You guys might be putting it in there, but I don't want to go too terribly slow so that we don't. Oh, there we go. When energy changes form, it loses ability to do work. Entropy is increasing. Nice. I like that vocabulary word. So there's always going to be less energy available at the end of a transfer process than at the beginning. In every energy transfer, there's going to be some energy that's lost. We don't really mean lost. It's just typically transformed to heat, which is often unusable. Okay. So thinking about those laws, why does it take a lot of hectares to support a pair of eagles in a wetland area? So this was part of an FRQ. It might feel a little bit out of the blue because I didn't put the whole thing in there, but why would it take a lot of land area to support eagles? Thinking about those laws of thermodynamics. And hopefully you're thinking about every time we have a change of form of energy from one trophic level to the next, it's going to, because of the 10% rule, only 10% is going to be transferred. So when we look at successive trophic levels, at every single level, we're going to have some energy lost as heat. That means it's a less usable form. And there's also, and these were all acceptable answers in this FRQ, some biomass is not going to be digestible. And so that's also going to mean that we need a larger area to support these top predators like eagles. When you're answering these, since most of you all, it sounds like you're going to be doing paper pencil, remember that I'm pretty picture oriented. So if you're going to draw a trophic level to explain it, you can't just draw the trophic level. You'll also need to accompany that with some sort of a prose explanation. Okay. Let's take a minute to calculate some efficiency. So part of energy is how we use it, and efficiency is going to play a role in the calculations that you see. So if we have an incandescent light bulb that's used for lighting and it has an efficiency rating of 5%, think about what that means for every joule of electricity consumed. So which of the following A, B, C, D, or E is true? Sarah, I think we might have a student that's waiting to be let in. And I can't see from my screen without stopping my screen share. If you could let her in, that'd be great.
Yeah, she's in.
Awesome.
I think
Thank you.
everyone's in. Yep.
Perfect. Okay, so what do you think? A, B, C, D, or E? And I've got a D is a potential answer. That's absolutely correct. And if you have studied these light bulbs, maybe you've even done a lab with these light bulbs, you know that the incandescent bulbs are the least energy efficient. So 90 to 95% of the energy the electricity that goes into lighting up that bulb is lost as heat. It gets really hot. CFLs are a little bit more efficient, or maybe a lot more efficient. And then LED is the most efficient. And you've got some watt comparison usages there. Okay, keep in mind on this exam that electricity is a secondary energy source. So my students recently completed a free response for me, and I asked, the free response asked, how can we reduce our dependence on petroleum? And a lot of them said, we can get away from fossil fuels if we use electric cars. That's a bit of a problem. Why is that not a great way to get off of fossil fuels? Just to answer, use electric cars. And feel free to use your mic instead of text if you'd like.
Because generally electric cars require energy, and for that to be stored up and produced in the first place, most fossil fuels are what we use to produce electricity, particularly in the US. So it wouldn't be likely that using electric cars would reduce our fossil fuel consumption. It would just be indirect.
Nice. And I usually say to students, if you've got a solar panel on your house and it's charging your electric car, then all right, you may be off fossil fuels, but you seem to understand that. You said that very well. In the United States, fossil fuels are powering our electrical grid. So it's still powering your car, even though it's plugged in. So that's the idea behind electricity is a secondary energy source, and primary energy sources are generating the electricity. So can somebody name the fossil fuels? What those three include? And again, feel free to use your mic or type, whatever you're comfortable with. Natural gas, petroleum, coal. Awesome. Those are all considered non-renewable, as I'm sure you know. There's a fourth non-renewable source that's not a fossil fuel, but still non-renewable. Can you tell me what that is? Nuclear. Excellent. So we can generate electricity with any of the non-renewables. What are some renewable energy sources you've talked about this year? So any renewable energy source you can think of, there's so many. Wind, geothermal, solar, hydroelectric, hydrogen power, awesome. Tidal power, we could also list that one. Could any of those solely take over for, say, coal or nuclear on our electricity grid? And again, if you wanted to turn on your mic and answer, that might be easier in some ways.
Didn't want to cut people off, but I don't think one alone could ever do it. Some areas don't have as much sun exposure, like say out in the desert, as compared to the Canadian areas, and hydroelectric doesn't work for every place. Again, in the desert, hydrogen power only works, but hydrogen can be dangerous in terms of transportation. And again, wind power varies, so I don't think we could ever have just one to replace fossil fuels.
Good. And coal and nuclear power plants are known as our baseload plants that run all the time. And then we typically are bringing in renewables to, make up the difference, or we're using natural gas or a diesel-based fuel. Yes, so we'll probably be looking at a combination of fuels in order to replace that. Okay. Speaking of nuclear and power plants, on the exam, you can expect a diagram of a power plant. This diagram has some labels on it. You should be able to label a blank one. That's kind of one of the skills that I always ask my students to do. But based on this diagram, which processes provide the energy to generate the electricity at this power plant? D. fission of radioactive fuel. Absolutely. So, oops, I didn't mean to go way past that. You should be able to identify, okay, these are control rods, these are fuel rods. I can see there's a containment structure here, and that is something you'd only find in a nuclear power plant. I usually contrast this with a coal-fired power plant. So as you're studying energy sources, you know, you need to be able to compare them, but make sure you understand how they work, how these power plants work. Nuclear and coal and biomass and petroleum or diesel or natural gas. Those are all considered to be thermal power plants because we are heating steam to turn our turbine and generate electricity. Okay, here's an FRQ practice. As conventional sources of crude oil are depleted, unconventional sources such as oil sands, also called tar sands, are being utilized. Oil sands contain bitumen, which can be processed into a synthetic crude oil. And maybe you're familiar with the oil sands are locally found in Alberta, Canada. That's where they are in North America anyway. And they've got a huge oil sands area where they're extracting bitumen. The deposit there contains 73 billion barrels of recoverable bitumen, and the rate of extraction is 1 million barrels of bitumen per day. And whether you're taking this online or on paper, I really highly recommend that you pull those numbers out because when they give you numbers like that, they're going to usually ask you to use them. So in this, calculate how many days will be needed to extract the recoverable volume of bitumen from oil sands. And I'll give you a minute to practice with this. At that extraction rate, how many days will be needed to extract the recoverable volume of bitumen from oil sands? You can definitely have your calculator handy for this. Okay, I've got 730 days as a possible answer. Let's take a look at that. So I would go ahead and convert the 73 billion to scientific notation. And we're going to divide that by our million barrels. And it's 73,000 days. So 730, pretty close guess. We just need to add in a few zeros there. Scientific notation, even though you'll be using a calculator, I think is your friend. So remember that billion is times 10 to the 9 and million is times 10 to the 6th. And I would recommend using that. When you are dividing by 10 to the 6th, remember that you're going to subtract it from that 10 to the 10. So 10 minus 6. And that can help you get those 7.3 times 10 to the 4 days. All right, the next part of this question. Oops. And for some reason, I don't know how to use my computer. Okay. Assuming the above extraction rate, calculate how many days will be needed to extract that amount. So we're going to take this 73,000 days, and then we're going to calculate, how many years. And I guess I didn't have these on a separate, I didn't give you an opportunity to calculate that one. I don't seem to have it on a separate slide. I wanted to point out one of the reasons why I included this question is if you get your days wrong, so you're just taking those days and dividing by 365, you can still get the second part of this right because the readers will take the number of days that you originally calculated, divide it by 365 and check your math. But if you did this correctly, you should have 200 years, and then we'll build on this again. How many, sorry, Ken, I seem to have included the answer here, but monthly production of synthetic crude oil is 30 million barrels. And that we can produce 1 billion of synthetic crude oil using 2 barrels of heated fresh water. By the way, this is a huge issue with using bitumen. Is it's very water intensive. So advantages and disadvantages are a pretty important part of this unit as well. So in this question, we're supposed to calculate the number of barrels of fresh water needed each year to supply demand. And so we're going to take that 30 million, which is 30 times 10 to the 6th, or 3 times 10 to the 7th. And we're going to multiply it times the number of barrels of fresh water needed. And we're looking at that over a 12-month period because they do ask us how much is needed each year to supply this demand. Again, when you're doing this on a laptop, it's important to make sure you know what your units are supposed to be in. And the dimensional analysis that's shown here helps you know, okay, I'm going to have to multiply by 12, for instance, whatever units I get here. I'm going to multiply by 12 to get the total amount of water needed over that 1 year period. But you can see that my units for synthetic oil are going to cancel out. My months are going to cancel out. And then I end up with barrels of fresh water per year, which is what the question calls for. So 3 times 2 is 6. And then I multiply that 6 times 12, and that gives me 72. And then I just need to account for my times 10 to the 7th. So 72 times 10 to the 7th or 7.2 times 10 to the 8th are all good. You are welcome to leave everything out of scientific notation if you prefer. So you can write all those zeros down. I would just recommend that you consider you're going to have to double check your numbers. Make sure that you didn't mess up on any zeros, which is why I kind of prefer scientific notation. Are there any questions about this one? I apologize that I didn't have it set up so that you could complete the calculations easily. Any questions about how we did the setup for this before I move on? Okay. All right. Reading a graph is a really important skill, and you can expect to see some graphs on there that you need to interpret. So this question says, based on the data in the graph, which of the following represents the total electricity production in the US from all energy sources in billions of kilowatt hours in 2017, which is the year this is taken from? Based on the data, which of the following represents the total electricity production in the US from all energy sources in billions of kilowatt hours? And feel free to make a guess. This is definitely a question that's going to have you doing a little math. And I'll walk you through this as you're thinking about it. So there are 2 lines here. We have the percent of total energy and we have wind generated electricity. And so our percent of total energy that is wind is 6.5%. And then the amount of energy in kilowatt hours is about 250 billion. And so those are the numbers that we want to use to do this calculation. So if you take the 250 billion and divide it by the percent, 0.065, then that tells you that the total amount of energy generated is 3.8 times 10 to the 12 kilowatt hours. So, so from this data, we can calculate, how much is 6.5%, knowing how much that is of the wind. How can we go backwards to determine how much total electricity is being generated? Any questions about that?
Wait, why do we use the wind? Because it says which of the following represents like the total electricity production. So I was just confused on why we started using the wind.
Sure. So they only gave us the amount of wind energy that's generated. And what this is saying is 6.5% of the total electricity is wind, and that 6.5% is equal to 250 billion.
Oh, okay.
Does that make sense? So they could have said, they could have given us the 3.8 times 10 to the 12 and then said, okay, if wind is 6.5%, how much is that? And we just would have multiplied by 6.5. But we had to go backwards. They're tricky like that. Thank you for asking. All right, let's take a look at another one. We have a family of 4 in a 3-bedroom house, and they use an average of 900 kilowatts of electricity per month. The family cools their house for 3 months during the summer with 2 window unit air conditioners that each use 350 kilowatt hours of electricity per month. Which of the following is the percent of the family's total annual electricity that's used to run those 2 air conditioners for the 3 summer months? So we have a lot of data in there. Again, I encourage you to pull out those numbers as you're thinking about this problem, and I'll give you a moment to give it a shot. You might want to think about, you've got information there to see what the total amount of electricity used for those unit air conditioners is. And that's on a per month basis. And then you have enough information there to calculate how much electricity they're using per year. This is a great question too, because we know that air conditioners, we can heat our home in a lot of different ways with natural gas or electricity, but with air conditioners, we can only use electricity. And that can be a big part of our energy use. Okay, let's break this question down a little bit. So we can calculate the total amount of electricity the family is using over the course of the year. We can also calculate those 2 units, each one using 350 kilowatt hours times 3 months. That tells us over that time period, they're going to use 2,100 kilowatts of electricity while they're running. And so to do percents, remember percents are always part over whole. So that part is 2,100 over the whole, which is all the electricity the family is using, and that's 10,800. And then I'll multiply that by 100 just to get my percent. And it ends up being 19.4%. Okay, so you will want to be confident about calculating percents. And I think it does help to think of it as part over whole. Any questions about how that calculation was done? Okay, let's take a look at the next one. An individual has been driving a passenger vehicle to work, and they're averaging 60 miles a week in a car that averages 22 miles per gallon. So those are obviously going to be pretty important to us. 60 miles per week, 22 miles per gallon. The individual plans to purchase a hybrid vehicle that averages 50 miles per gallon. If the individual drives to work 50 weeks a year, how much gas will they save if they switch to that hybrid vehicle for their commute? So let's see if we can calculate it. As you may already be thinking, we need to see what the original car, how much gasoline are we using with that one? And then let's calculate it for our hybrid vehicle. So we're commuting 50 weeks per year, 60 miles a week, 22 miles per gallon. And again, if you're using dimensional analysis to set this up, it's going to be pretty helpful. And once we get the amount of gallons each one is using, we can do some subtraction there to see how much they'll save if they switch. I've got an answer. Let's check it. All right, it is indeed C. So our original car, 60 miles per week, and it's using 22 miles per gallon. We're going to multiply that times 50 weeks. It will use 136 gallons. That same setup for our hybrid is only going to use 60 gallons of gasoline, so they will save 76 gallons. Any questions about that one?
Do we always like have to use dimensional analysis? Like, will it always sometimes specify? Because like I've always been more of like a person that like does an academic team style where you just like take in as much information, you scribble it out as quickly as possible.
I think for complex questions, it's a good way to make sure that you have the setup right. I highly recommend it just because of the of that setup piece, and it's, you know, it's going to make sure that your whatever your end units are going to be, they're going to be the right ones, what you'd expect. As far as what the College Board looks like, I think that strategy of I'm going to quickly do it as long as you're accurate, that's great for multiple choice. But when you get to the FRQs, they're going to require that showing a setup. They definitely want you to have units on your final answer, but they need to know what you multiplied by what. Sometimes you can get away with not putting the units in there, but I always think it's a good idea. So that was maybe a long-winded answer, but but that's what I would recommend. You've got to show your work when it comes to FRQs, no matter what. Okay, let's take a look at this question. So now we've been given a graph, a little pie chart here, and notice that there's data up at the top there. So in addition to the different percents, it says total consumption is 97.7 quadrillion BTUs. Don't let a number by quadrillion intimidate you, because it's not all that important that you know what it is. You don't need to convert it into scientific notation or anything. How many BTUs were consumed in the United States in 2017 by consumers that used petroleum as a fuel source? Grab your calculators. See if you can figure that one out. Thanks for that, Sarah. I'm not sure if you all saw it in the chat. There are questions on the multiple choice that want you to pick the setup, and you don't even have to come up with a number. Okay, I've got a possible answer here. Is it B? It indeed is. So in order to get 36 quadrillion BTUs, we're just going to take this 97.7 and multiply it by 0.37, which is the 37% is the amount of that total consumption that comes from petroleum. So well done, ISIS. Okay, half-life questions. So half-life is being able to manipulate that and kind of understand it's going to be important. I would expect at least one multiple choice question on this. After 200 million years, only 1/16 of the original amount of a particular radioactive waste will remain. The half-life of this radioactive waste is how many million years? Any guesses? Or maybe not even a guess, just I know for sure that this is what it is. Okay, I see a couple that are A. Any other guesses? And I'll give you guys a strategy to deal with the half-life questions. C, indeed. Oops, let's go back one. Yes, it is in fact C. So I usually write down on my paper, you know, this is my original amount. One half-life, I've got half of that. Second half-life, I've got a quarter of that. Third half-life, I've got an eighth of that. And my fourth half-life, I've got a 16th of that. And that's what they're asking me about. How do I get down to a 16th? And it's going to take 4 half-lives to get there. And so 200 divided by 4 will give me 50 million. And I really, this is where I wish we were all together and I could write on the board and kind of show you how I do that half-life calculation. But that's one strategy that works for me. Any questions or comments? Anyone have a different strategy that they prefer for answering those questions? Okay, and maybe you found it, fairly easy. So when you're looking at energy types, I said this earlier, but I just think it's the best way to study energy. You want to make sure you know how it works. You want to make sure you understand the advantages and the disadvantages of them. And then you want to be able to compare and contrast. And remember, for most questions, you don't have to know every single advantage and disadvantage for all of them, but you should know some of them pretty well. So, but this kind of a setup as you're studying is helpful. So let's put a little bit of that into action, especially the compare and contrast. So here's a huge block of text, which I'll read to you. So Marcellus Shale is a large domestic natural gas reserve that could meet the U.S. energy needs for 25 years. The 350 million year old geological formation stretches from New York to West Virginia on land that is largely undeveloped. It was once thought it was too difficult to extract natural gas from Marcellus Shale, but new drilling technology allows energy companies to tap this vast reserve. The natural gas is removed by a process called hydraulic fracturing or fracking. During this process, the shale is drilled and millions of gallons of water, sand, and chemicals are pumped into the shale at high pressure, shattering the shale and releasing the natural gas trapped within. While some of this water remains below ground, contaminated water is also stored in ponds, trucked to wastewater treatment plants, or disposed of by spraying it on nearby land. Identify and describe. So notice that the use of those words, identify and describe, 2 water-related environmental problems associated with fracking. Identify and describe 2 water-related environmental problems associated with fracking. So you don't necessarily have to describe them in the chat, but let's see if we can at least identify them. So throw in 1. Maybe we can together collectively come up with 2. Groundwater contamination, nice. And we might, if we were describing groundwater contamination, we might talk about what it's contaminated with. Any other guesses?
Just a question, would runoff and poisoning of plants and other things that would take it in count?
Well, let's look at the key. So that's kind of the effect, part of the effect that you're going from there. I would probably want to lead in, if you look at the second one, surface water contamination. You want to explain, how the water is going to contaminate those, but I don't know that the plant one would necessarily fit. So groundwater is contamination is coming from either leaks from the methane or fracking liquids that end up contaminating the groundwater, waste leaching into groundwater, radioactive isotopes that are in the fracking fluid. So our identification is on the left, and then on the right is our description. So you might be able to say something like the spraying of that material in surface water is going to contaminate streams, and then you could tie that in with plants, or plants contaminate soil and you could tie it in that with plants. But I don't know that I don't think that fits this one in particular.
Okay, because I just saw that as being a major problem, because even if the plants got contaminated, that could lead to biomagnification somewhere later along the line with humans.
I see where you're going with that. I think for this one, we have to get it into a waterway or to groundwater in order to make that connection, just because of the way they worded that. So those sound like they might be possible effects. With bioaccumulation, remember, that's mostly we talk about that in waterways, but definitely, it's one way that people could be exposed to toxic material if it was taken out by the plant and then the plants were harvested for food. Let's look at another component. So natural gas is considered to be a better fossil fuel for the environment than coal. think about comparing these two, discuss two environmental benefits of using natural gas as a fuel compared to using coal. So this is kind of that compare and contrast piece. So tell me something about natural gas. Less CO2, less NOx emissions. Good. So probably you guys have done that activity where we're ranking fossil fuels in order of how dirty or how clean they are. Coal is definitely considered the dirtiest. It releases the most carbon dioxide. Anyone else? Another difference between those two. Good. We can think about how they're harvested, less threats to miners for sure. Let's take a look at some other possibilities. So one of the things that you want to be careful of is, again, if you're doing this on paper, underline environment. And no one, I didn't see this in the chat, but you can have some economic impacts also, but this is going to focus on environmental. So fewer NOx, that works. Fewer SOx, that works too. I would get in the habit when you answer FRQs to also make the connection between what environmental issue, those result in. So the less sulfur oxides and nitrous oxides that we have released means less acid rain, and NOx, less photochemical smog. There's less mercury released when we burn natural gas as compared to coal. And Tina, you said threats to miners, that's listed. Harmful mining techniques are avoided. So we don't have, I think you could totally list, we don't have, mine collapses. Of course, they mentioned the surface mining issues, but I think you could make that argument for mine collapses. There are fewer particulates and there's less carbon dioxide. Okay, so you don't have to know all of them. You just need to know a few of them. Describe two environmental drawbacks not related to water use of using the fracking process to extract natural gas from shale. Two environmental drawbacks that aren't water related. So this might be where we can talk about plants. So any other environmental drawbacks you can think of before we take a look at some possible answers? Biocontamination. Yeah. All right, let's see what else. So lots of possibilities. You only needed to name two of these. That third bullet, methane can leak into the atmosphere, resulting in an increase of greenhouse gases. Remember, methane is something like 25 times more potent a greenhouse gas than carbon dioxide. So that's a pretty big environmental drawback. Habitat fragmentation from setting up the drilling site. Again, we want to make sure we're describing, so we can't just say habitat fragmentation, but we have to explain what that connects with. Earthquakes can result from the drilling or the fracking process. There's some good evidence that the earthquakes are probably from injection of the wastewater back into the rock, but that would be appropriate. Subsidence of the land can occur once the fracking fluids are removed. And you can think about the impacts of the trucks and the drilling equipment. They're using a non-renewable fuel, likely using petroleum, and they're releasing carbon dioxide, potentially SOx, NOx, and then we would want to, as you can see there in parentheses, we need to connect that. Releasing CO2, it's a greenhouse gas. It's going to contribute to climate change. Releasing SOx, it's going to contribute to acid rain formation. So just make sure you're making those connections because this is a described question. Noise pollution is caused by the drilling rigs and by increased truck traffic. Soil salinization or heavy metal contamination can result from the spraying of wastewater. Ding, 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 there's our plants connection. The drilling site increases the amount of particulate matter in the air. And then there could be other possibilities. So this is just, keep that in mind whenever you look at these scoring guides. And students especially, ask your teacher, is this appropriate? Am I thinking about this in the right way? If it's not on the scoring guide, it can still be an appropriate answer. All right, now they want economics. So again, on paper, underline economics. Describe one economic benefit to society of using fracking to obtain natural gas. And I seem to have not given you an opportunity to answer, but you could have put creation of jobs, fairly straightforward. When we are developing a domestic energy source, we don't have to import as much foreign fuel. And then if you are an individual who has natural gas on your property, if you're on the Marcellus Shale Formation, then you're going to economically benefit from allowing companies to collect natural gas on site. Okay, so there's lots of good ways that you can practice the FRQs related to energy. So yeah, so make sure that you do that and you're thinking about those advantages. Okay, they often throw in, so we've been talking about fossil fuels and natural gas. It's really common on these FRQs for them to switch gears. Nuclear power is an alternative to using natural gas or coal as a fuel for generating electricity. So now they want us to tell them something about nuclear power. There are also problems associated with nuclear power plants, and they want you to describe 2 negative environmental impacts associated with nuclear power. So tell me what you know about nuclear power. And I'm going to go ahead and, I don't see anything posted in chat. I'm going to go ahead and give you some options. So storage is a biggie, and that hopefully is one of the first things you think about when you think about the issues with nuclear power. Storage and accidents, are the 2 most common. So spent nuclear waste, we don't really have a storage facility for high level waste. And it has to be stored for 10 half-lives in order to be considered safe. So that's a major issue. Nuclear accidents or plant failures would release radioactive material. And then maybe some of the less big ideas that come out to you. Thermal pollution from any thermal plant. We can impact surface waters if we're dumping water that's warmer than the environment out into that stream or river. Contaminate soil, water, air, and living organisms. That's the nuclear accident. Sorry, it should be a separate bullet. Mining of uranium is going to have environmental impacts. And of course, you would need to explain habitat degradation, radioactive mine tailings needing to be dealt with, etc. Uranium is also considered a non-renewable resource, so it has a finite life. Plants that decommission have to somehow be dealt with because they are radioactive themselves. Runoff during construction, waste produced during enrichment, and then nuclear energy production is less efficient than a coal burning power plant. Most uranium ends up as waste. Interestingly enough, if you've ever seen the comparison with the amount of uranium it takes to produce the same amount of power as coal, it takes a whole lot less uranium, but still it's not necessarily efficient when used. Okay, that is it, friends. I hope that that was a helpful review for you about some of the topics you need to know for energy flow, for power plants, renewable, non-renewable energy. It's not complete, but it's a good start. Do you have any questions or comments for me before we take a break and Sarah Nolen takes over? Okay. My watch says 1:29. Why don't we take a 5-minute break, get yourself something to drink or snack on, go to the bathroom if you need to, and we'll meet back here at 1:34. Does that sound good? All right.
Okay, can you guys see that and hear everything okay?
Yeah.
Okay, then we're good to go. Okay, so guys, this is it. This is your last study session. So here we go. So we're gonna finish up today with Unit 8. Unit 8 is a rather large unit in itself. With Unit 8, we have aquatic and terrestrial pollution. And give me just a second here. I'm gonna figure out why. I can't see the chat over here. Yeah, I can't now. Okay. So we're going to see what we can get through in this hour. Basically, what I did is I went through and I tried to go through like as many topics as I could for this unit. So we'll do kind of a brief little review, and then we will do some multiple choice practice with it to kind of, keep you engaged and help you get ready for that exam that you take in a couple of days. One thing that might help you if you haven't been doing this already with your teachers, and many of you have, but is to come up with a chart. And I make my kids handwrite it. One, because many of you are about to maybe take the exam that may be handwritten, and sometimes we need a little practice writing. It's been a long time since we've written anything. And two, the research shows that when you write things down, you're more likely to remember it. And this year has been really hard on all of us, having to type everything, and everything is online. And sometimes it's good just to kind of step back and write things down. But as we go through the pollutants, and as you review your pollutants, I actually make this just an assignment for my students. I have them write down the pollutant, what are the causes, what are the sources, what are the consequences, and then of course, because sustainability is a big emphasis in this class, what are the solutions then? So if you would like to jot some of those things down today, as we go through a pollutant, you're like, oh yeah, I forgot about that one. That might be something to do, and that way you kind of have it in your toolbox as you review this final week. Okay, so as we go through the pollutants, remember some of them are point source pollutants, some of them are non-point source pollutants. And the difficult thing about pollution and human health is that there's so many factors that we come in contact with, and we're exposed to so many kinds, whether it be air pollution, aquatic pollution, terrestrial pollution. And that's another thing about these units too. They do kind of get jumbled and confused, especially after you've learned so many. Once we've come to this point in the course, I always tell my students that it's good to have a toolbox of specific pollutants to talk about, because if you just use the word pollution, let's say in an FRQ, you're probably not as likely to get the points as if you pointed out a specific pollutant. A lot of time they're looking for specific pollutants. So again, going through that chart, making that chart, keeping all of these, sorted out in your brain will help. Okay. Remember, some are point, some are non-point. If you were with me in one of the review sessions before, you would know that, we talked about the point ones. I think we did this back in the air pollution. The point are the ones you can point to. The non-point are the ones that are a little more vague, a little more common, like cropland, runoff, things like that. Okay. Another thing about aquatic and terrestrial pollution is that we can't just focus on the humans. Yes, that might be part of something that asks you in a multiple choice or an FRQ question, but we also have to consider the wildlife, and that the reason why we study pollution, rather whatever the type is, looking at the effect on ecosystems, is it ties in concepts like ecology and even natural selection, that organisms have this range of tolerance, and that those, that are kind of on the edge here, that, in the zone of stress, they might not be able to survive. I'm sorry, the ones in the optimum may not be able to survive. And then there's very few species out here that would. And so this shows you that organisms need to have a specific or a range of tolerance, and that when these pollutants get thrown into the aquatic ecosystem or the terrestrial ecosystem, that it's stressful on their ability to survive. Okay. Real quick, before we get into the specific pollutants, remember, how do we come in contact with them? For humans, whether it be these chemical risks or these biological risks that we come in contact with, it's a variety of sources that we are constantly being exposed to in the air, in the water, in our food sources, pests, disease, wild animals, our food source, even pets are in our own home. can transmit some of these biological risks to us. And then we can transmit them to other humans. And then, of course, the mothers, the pregnant mothers, to the fetus and the babies. And as you know, we still are in a global pandemic. So a lot of the biological risk part of this unit, you guys have definitely learned firsthand for sure. So if there's any questions about pandemics or biological risks, I would say this year you guys would probably do pretty well on those. Okay, so let's do a little warm up here. I know this is a pretty simple question, but that way we can test and make sure you're all with me and try this out. So of the following, which is the best example of a point source of water pollution? So we're going to talk about two different types of sources of pollution today. So which one here is going to be the point source of pollution? Okay, I see an A. Anyone else want to take a guess? Okay, well, if you guessed A, you're correct. So good job, guys. All the others are non-point. So as we go through these different water pollutants, many of the causes or the sources are going to be things that are a little more vague and very hard to pinpoint exactly where the source is coming from. So good job. Okay, so let's start with one of the topics in Unit 8, biological risks, the pathogens and the infectious diseases that we come in contact with. Some of these may be transmitted to us through humans and animals. Some of these can be picked up in the water. So diseases that you'll need to know, as outlined by the College Board. There's a list of them. I tell my kids, we're not trying to get you a medical degree, so you don't have to know all of the symptoms of it and be able to diagnose someone, but you do at least need to be familiar with these things like plague, tuberculosis, malaria, especially when we're talking about mosquitoes. Malaria, West Nile, Zika are all those that are associated with mosquitoes. And when we talk about mosquitoes, that brings in climate change. And how I always say that while climate change may not be great for some organisms or lots of organisms, the mosquitoes love it. So that ties in other concepts like the climate change and what's that going to do to disease. Respiratory infections like SARS and MERS. Waterborne pathogens like cholera and dysentery. And so again, just kind of having a general idea about some of these and other things that they'll ask you or they've asked in the past. May not be specific questions about them, but more, as we are a global society, things like how do new strains come about? I think we're all living that right now. Pandemics. Again, if there's a question about anything dealing with a pandemic, you guys are going to be the year that hopefully you all get that question right. Maybe that's one of the silver linings of this, but climate change, disease, poverty, sanitary conditions, disease control. So any of those are fair game when it comes to that. So are there any questions specifically about that? And like I said, we're not trying to get you a medical degree here, but just at least in general know how this happens. Okay, another pollutant that we'll discuss, endocrine disruptors. Endocrine disruptors are chemicals that affect specifically a certain system, the endocrine system, and that deals with your hormones, that deals with things like reproduction. And so the consequences are going to be possible birth defects, developmental disorders, gender imbalances. We come in contact with endocrine disruptors, some of the pesticides, BPAs, if you look at any of your bottles, you might notice that sometimes they say BPA free. And so as we are finding more and more about these endocrine disruptors, we're finding that a lot of them are linked to some of the things we use in our plastics. And so that's why I put for the solutions like source reduction, maybe find alternatives to that. If you haven't heard about the story of the frogs and atrazine, that's a case study to maybe look into. That's kind of where a lot of the research has kind of started with, I want to say his name is Tyrone Hayes. And he did a lot of work studying atrazine and what effect it was having on the frogs. And they were finding that frogs were having testes and ovaries. But with the amounts, they never were able to, block atrazine or take it off the market because there wasn't enough data about exactly what amount. And that kind of brings us into another topic that we'll talk about later, like the LD50 and the dose curve responses and things like that are also in this unit. Another thing real quick to kind of review real quick, another pollutant are persistent organic pollutants, the POPs. This may be things like PCBs and DDT. These are ones that can travel long distances and they are soluble in fat. So that means that they will stick with your fat. And so therefore, the older the organism, the more fat the organism has, the more likely that these chemicals are going to stick with that organism as it moves through the food chain. And so that brings up things like, biomagnification and bioaccumulation as well. Okay, so let's take a little pause here. Try some multiple choice. So which of the following best explains why DDT has been found in penguin eggs in the Antarctic? And so this one talks about talking about those POPs here. Any guesses? Okay, I see a few popping up. Very good. A. This is just to show you that when we do study these things, we are, a global, sorry, that I got a cold or something going on here. That things do circulate and that there is no just bubble right over us. And it's not like our air pollution just stays right above America. And it's not like our water pollution just stays right in your backyard. Things do circulate. And so even when things like DDT, which has been banned in America, that doesn't mean that it hasn't been used in other countries. That doesn't mean it can't circulate. That doesn't mean that it can't come right back into your grocery store on plants that have been grown in other countries. So again, yes, we do have to think of the big picture there. So very good. Okay, let's try another one. While scientists discover the existence of an emerging infection disease such as SARS, they must take immediate steps to determine the cause of the disease and the method of transmission. These initial steps would include which of the following? So guys, if nothing else, think back to what did we do in the beginning when COVID-19 hit? Okay, I see a C. See a D. Okay, the best answer here is C. That while eventually when we do look at those biological risks and those pathogens, many of these things will happen, like develop a vaccine. That's where we are now with this. But the very first thing that we did in the beginning, or the CDC did in the beginning and the World Health Organization did in the beginning, was try to figure out where it came from, and then the whole, contact tracing. Basically, C is another way of saying contact tracing, which we're all aware of now. Okay, factors that increase the spread of infectious disease include all the following except. So if you are going to get an infectious disease, which one increases the spread of or does not increase the spread? Okay, so we have flooding, global warming, introduction of insect vectors, exposure to neurotoxins, rural poverty. Okay, so I see a C, see a D. Okay, so let's look at D. Exposure to neurotoxins, which affect the endocrine system. First of all, D is the correct answer, but what do neurotoxins affect? So what else would help you figure out why this is not the best answer? You want to put that in the chat or unmute your mic, whichever's easier for you guys.
Neurotoxins, so it would affect the nervous system, right?
Very good. So even if you weren't sure about A, B, C, and E, you could look at that one and be like, well, no, neurotoxins affect the nervous system. So very good. Okay. So just a little tool to help you there on that multiple choice. Okay. So let's kind of get back to a quick little review here. So also in this unit, you learned about bioaccumulation and biomagnification. Those are two that are very easily to get confused. So hopefully maybe I can help you separate those two concepts real quick. Biomagnification is talking about the food chain, and that as you go up the food chain, that you can see over here, the biomagnification, the contaminants increases. So if you had a contaminant, so whether it be the DDT or the PCBs, mercury, some of those heavy metals that biomagnify, then as you go from the producers through the consumers, that the ones at the very end are getting most of the poison. So this is actually the opposite of what you just learned back in your trophic levels. Okay, so it's, with energy, you talk about the energy decreasing in quality, but when it talks about the chemicals and the pesticides and the pollutants, many of them will increase as you go through the food chain. Now, bioaccumulate is talking specifically about time, and it also references how much fat the organism has. So the older the organism, the more fat tissue on the organism, the more time that chemical has had to accumulate. So in other words, they're not soluble and they're not leaving through their waste like urine, they're accumulating in their body. So if those metals are accumulating, and then you also throw in the fact that they're higher up on the food chain, that's why many times bioaccumulation, biomagnification kind of go hand in hand. But they are two separate, but a lot of times they are talked about together. So biomagnify, we're magnifying as we go through the food chain. Bioaccumulate, just think about, as you accumulate junk throughout the years, you accumulate it, it builds up. So in this case, not only are you accumulating all kinds of things throughout your lifetime, knickknacks and, material items, you're also accumulating all of the toxins that are accumulating in your body as well, if they're not leaving through the water of your body. DDT, this is one that I would definitely know for sure. And I'm sure your teachers have talked about it and you've heard about it. It's one of the more widely known pesticides. It used to be used widely in the United States, and Rachel Carson kind of helped bring that to an end with her book Silent Spring. Does anyone want to kind of throw out in the chat box why we no longer use DDT? Like what was kind of the event that happened here, talking about Rachel Carson? Or again, unmute your mic, whichever one is easier.
Didn't it hurt the eagles by making their eggshells less firm, so whenever incubation occurred, they cracked? Also in smaller birds, she saw studies of where the birds died shortly after DDT had been applied to the area.
Yes, very good. Excellent. You have some excellent answers today. And yeah, so that was definitely one of the cases there, looking at that biomagnification. And then other studies have shown that DDT was in fact a carcinogen. And so that's why, these are also just kind of pictures to think that we've come a long way. They would just go through beaches, go through neighborhoods, spray DDT. They still do use DDT in other countries, especially for malaria control. If you have done the little story of the cats of Borneo, that, starts out with the story of they sprayed DDT and then all of the chain of events that went along with it. So even, DDT kind of pops up in a lot of our little case studies in environmental science. But that is one that's used a lot as an example of a a pollutant that is going to biomagnify and bioaccumulate. Mercury is another one that I would definitely know. Mercury enters through the aquatic environment, and then bacteria actually convert it to the very highly toxic methyl mercury. So where is most of the mercury coming from that you're going to come in contact with? In fact, it's going to come from the coal burning power plants. So kind of tying into that little energy review you had earlier today. As it accumulates through the organisms, of course, then it's going to biomagnify as you move up the food web. And so what does mercury do to you? There's a whole list of things that it does. It can cause everything from kidney failure to seizures, skin problems, tremors. If you know the story of the Minamata Bay in Japan, that's kind of a good case study that is used to show the effects of mercury on people. They were dumping mercury just straight into the bay. And at first they called it the dancing cats. The cats were eating the fish. They noticed the cats were having, convulsions and tremors. But then they started noticing it in the people as well. And so this was a case where the people were eating the fish that had been exposed to the mercury through the food chain as it built up. Okay, so mercury is another one. That is why pregnant women are advised to limit the fish that they eat. That's probably a good idea, just not to eat any while you are pregnant, because of the small doses that affect the fetus. This is also why, there's a limit on how much fish anyone should really be eating because of the mercury amounts in those larger, especially one of those predatory fish. Okay, so let's do some multiple choice practice here. So which of the following is the best description of bioaccumulation? So lots of keywords we've talked about here, but let's see if we can pick out the best one. Okay, I see a B. Okay, a couple B's there. Very good. It's the fact that you are absorbing it faster than you can eliminate it. Okay. And so you're going to see some of these other buzzwords that we've talked about that are meant to throw you off. But just kind of make sure you slow down and you read through all the questions as you're choosing the best one. So very good. Many synthetic chemicals, such as PCBs, act as estrogen mimics. In an ecosystem, these persistent chemicals would have the greatest effect on which of the following? So if you are going to be exposed to one of these pollutants, which one is it going to have the greatest effect on as an organism? Okay, I see a D. Very good. And this goes right along with what you learned in the first part of the study session. It goes back to those trophic levels. That yes, the secondary consumers, because they're going to be at the top of the food chain, they're going to have the greatest amount due to biomagnification. Again, another example just to show you that so many of these topics blend together that you've learned all year long. And so that even though this one was specifically from the water pollution unit, that if you didn't remember back to ecology about your trophic levels, then you'd have a hard time answering this. So as you're reviewing this week, make sure you identify which areas you're kind of weak in, and go back and review those. I know all of you have been on crazy schedules this year with NTI and hybrid and in-person, and maybe you're all still virtual or you're back in person off and on throughout the year. So it's definitely a good idea to kind of go back, especially in the beginning when you probably weren't face-to-face with your teacher, to go back and kind of review some of those earlier units this week. Okay, so let's kind of move on to another topic that I don't know about you guys, but my students seem to struggle with. It's not a difficult topic, I don't think, but there is a lot of, this is the one of the unit that involves a little more interpreting of the graphs, reading the graphs, and there's a little bit of math involved, okay? So all of these pollutants that we've been talking about, well, how do we know they're toxic? Or, are some pollutants more toxic than others? And yes, that in fact is the case. And so in this unit, you learned about lethal dose 50 and dose response studies. So lethal dose 50 is just basically how much dose, whatever pollutant, chemical, toxin we're talking about, it requires to kill 50% of the population. But then other studies may not look at the mortality rate. Other studies may look at how effective it is. It may look at other, responses of the organisms besides just if it dies or not. And so I always tell my kids, this is the case where, if you had to call poison control, they're going to ask you, okay, what's the size of the person? How much did they ingest? And that is what some of these, LD50 or effective dose numbers are based upon. Okay, so first let's understand dosage a little bit before we get into the math and the reading of the graphs. Dosage is how much you're exposed to. Now they can't just give people these chemicals. So what they do instead is they give rats these chemicals, and then they look at the response that the rats have. And one rat weighs usually approximately 1 kilogram. So if it says 2,000 milligrams per kilogram, that means that for the size of a rat, the LD50 would be 2,000 milligrams. That doesn't mean that all rats are going to die at 2,000 milligrams. It's just that's the amount that 50% of the rat population, when they got that dose, it had killed off half of the rats. So as you look at these numbers, I want you to take a guess, or which one do you think would be the most toxic? Okay, so I see a guess on the pesticide because it's requiring the smallest dose. Okay, any other guesses? Okay, that is in fact correct. You're looking for the number that requires the smallest dose. So in other words, for this rat population, it only required 4 milligrams of that to have the effect. But looking at like the detergent, you had to have way more than that, like 2,000 milligrams. And so looking at something like this, like the moisturizer, yes, you could kill half the population of rats with moisturizer, but it's going to take a lot of moisturizer. If you use the pesticide, which is in fact intended to kill the rats, we don't use lotion to kill rats, we use pesticide to kill rats, that doesn't require as much. Okay, so they would use this to look at things like pesticides, insecticides, and those would kind of be the applications that we would use for this. Okay, so how do you set up the math if it's asked you to set up the math? I noticed that this one was on one of the sample multiple choice questions not too long ago. So if you haven't done any practice with calculating LD50, it's pretty simple. And this was what I was talking about earlier in the chat box, that sometimes they don't even ask you to solve the problem. They're more interested in, could you pick out the one that has the best setup? So if this was the case, let's say a person was 140 pounds, well, you have to figure out how many kilograms that is, because the LD50 is measured in metric and kilograms. So in a lot of these math problems, you're going to have to go from our system to the metric system. And then knowing that it takes 13 milligrams for the rat, which is 1 kilogram, and then we have to convert it because that was in milligrams. Then it wanted to know what it would be in terms of the grams. Okay, so that's how you would set that one up. And here in a minute, I'll give you a multiple choice practice one where you have to kind of find the correct setup with that. But I at least wanted to kind of walk you through that one first and give you that example. Another thing you have to do with LD50 is knowing how to read the graph. And so if, let's say, let's start with this one. This one is LD50 of 2 species of mice. So if it asked specifically for the LD50, you would follow the 50 over. And so for species 1, you can see down here, it's about, let's say 500. For species 2, you follow that down, it would be a little closer to the 600 line. Okay, so maybe, I don't know, 590 or so. And so I have a question for you guys then about this graph. Which one do you think would be more toxic? In other words, a species 1 or species 2? Like, what is the difference there? So let me rephrase that again. So do you think species 1 or species 2, which one requires less of the exposure for LD50? Very good. Very good, because species 1, if you follow it down, would be here versus species 2, they require more of the exposure before they reach the 50% of them dying, okay? You might also see it here. This one is not specifically about mortality. This one is illness. And so sometimes they look at other types of responses besides just death. And so here you have different types of bacteria. And so they might use a graph like this to ask you which types of bacteria would pose more of a threat to a population, which types of these bacteria kind of looks like it levels off here. So maybe that one, you could do that. If we were talking about this bacteria here, I could say that this bacteria had more of a probability of giving you illness versus this bacteria here. Only about 20% of the population developed illness. And so that might be another example of a type of a graph that you might see with that, okay? Okay, so let's get into some multiple choice about those. So if we were looking at a laboratory study using rats showed a steady increase in physical effects as the concentration of a toxic substance in their food was increased. This suggests that what? So I'll give you a minute, let you digest that one. You want to put your guess in the chat box or? So as the toxic substance is increasing, there is a steady increase in the physical effects. So what type, how do you think that would look on that graph? Okay, I see I'm stuck on those. Well, let me help you with this one then. You are correct in the fact that it is D, the dose response relationship is linear. Okay, so what does that mean? It means that as one is going up, then the other one you're going to see that clear relationship with. So there's a very clear relationship that as the toxic substance is increasing, there's also the same linear increase in the physical effects. So if you were to see something like that on, let's say on a graph, that may be something that's a little more, with that linear, straightforward, like, oh, as this is increasing, that is increasing. Okay, so very good there. Okay, let's try another one. Here's another one where we're looking at concentration and we're looking at percent of induction. And this is looking specifically of responsive breast cancer cells to a specific, in this case, concentration of anastrozole. So which of the data, which is the best description of this relationship? And again, you don't really have to know anything about this specific chemical. This is more of a reading a graph. And I think this year you're going to see a lot more of that on your exam. And that's why I've been trying to throw some of these into the study session for you. Okay, so I see a B. Any other guesses? I'm going to give you all a chance here. Okay, so yes, very good. The answer is B. So as the concentration there is increasing, you can see that the percent is in fact decreasing. So very good there. Okay. Okay, and I just saw the comment, can you define threshold? So the threshold, and again, you know, correct me if I'm wrong or if another teacher wants to help kind of explain it a different way. It's the amount where you start to see that effect. And so, you know, some chemicals, kind of like this one, for example, it seems like the more you give the chemical, the less of the effect that you're having. Okay. Let's try another one. And this one ties in some good practice with the fact that on Friday, you're going to have to set up an experiment. That's going to be one of your FRQs. So while this isn't an FRQ, but it does see if you how well you are at looking at these experimental designs. So an experiment was carried out to determine the lethal dose of ammonium sulfate on mung bean germination. True statements about the experimental design include which of the following? The control group has neither the seeds nor the ammonium sulfate. The independent variable is the concentration of the ammonium sulfate, or the dependent variable is the number of seeds that fail to germinate. I'll give you a minute, kind of let that sink in. Try that out. Think about it. Okay, I see some D. Anyone else want to guess? And I see that Leslie is leaving. Ms. Campbell, you're very welcome. Good luck to you and your students. Yes, okay. So in the control group, guys, you're going to have at least some seeds, so that wouldn't work. You probably don't want to add the actual toxin, but you're going to need to have some seeds. So we can eliminate that. The independent variable is the concentration of ammonium sulfate. So very good. The independent variable in your experimental design is what you're going to change. And then the dependent variable, that is what you are going to count. So you're going to see the number of seeds that fail to germinate. And that in fact would show you the lethal dose, because that would show you that they died. And so therefore that's going to count in there. So very good. Okay, one more LD50 question. So for a certain insecticide, the LD50 dosage level for rats is determined to be 250 milligrams per kilogram of body mass. So based on that information, which of the following is the best prediction regarding the consequences of receiving this dosage to the insecticide? So this is really just asking you to define LD50. Okay, I see an E. Okay, so 500 out of every 1,000 rats would die. Very, very good there. Very good. Because that would be 50%. So very good. Okay, and this is what I was talking about earlier, why I wanted to help you set that one up about calculating LD50. This one asks you to not even, really, you don't even have to solve it. You got to pick out which one would be the best setup. Okay, I see an E. Any other guesses? Again, you only have to solve it. How would you set it up? Oh, sorry, that was for another answer. Okay. Okay, let me maybe help walk you through this one. So if you needed 55 milligrams, if you weighed 1 kilogram. Now, if that organism only weighs not a whole kilogram, but only 0.02 of a kilogram, now think about that. How would you set that up? Remember, they don't even weigh a whole kilogram. If they did, they require 55 milligrams. They weigh less than that. So clearly they're going to need less than 55 milligrams. Okay, yeah, so you would take how much, so you would take the 55, and then since you would then, divide that by how much they weigh. So very good. Okay, so any questions about LD50? Then we'll get back to some more water pollutant ones. Okay, so we got a few minutes left here. Let's kind of wrap up here with some going back to specific water pollutants that you will need to know on Friday. This one I wanted to make sure we definitely covered in our study session, eutrophication. Eutrophication will pop up a lot on your exam because it involves everything from agriculture to sewage waste treatment plants to the biogeochemical cycles of nitrates and phosphates. It ties in dissolved oxygen, it ties in dead zones. There's all kinds of things that will tie back to the topic of eutrophication. Okay, so eutrophication just basically means high nutrients. And so this is a major problem in lots of waterways because of our agriculture runoff and our wastewater release. So which specific nutrients are coming with agriculture runoff? If you want to throw that in the chat box, see what you guys know about eutrophication here. That's weird. There it is. Okay, we're delayed there. Okay, now it looks like we see that. Now do you see the eutrophication? Okay, there we go. Okay. So the eutrophication, back to what I was saying, what specific, like again, pollutant, nutrient, what are we talking about here in the agriculture runoff or in the wastewater release? Why do we need to worry about agriculture runoff or wastewater release? If you want to throw that on the chat box or unmute your mic, go for it.
The nitrogen and phosphorus fertilizers, well, the agriculture runoff sends them into waterways, which will accelerate like algae growth, but eventually they die, which causes like decomposers to decompose them, which increases the biological oxygen demand, which lowers the oxygen in the given area, resulting in a dead zone that few life forms can survive in.
Excellent. Very excellent response there. Yes, so with the excess fertilizers that we are putting on agricultural fields, it is running into the waterways. And especially in America, when we talk about the Mississippi watershed, there are so many little rivers and creeks that run into that watershed. And so all of these water, the water with these enriched nutrients are coming into the waterways, and then the algae eats it up. They love all of these extra nutrients, but all good things come to an end, and then the algae die. And then when the algae die, just like what you said, very good, the bacteria then have to then break down the algae because now they're excited that they get a food source. And as they are breaking down the algae, then they start to lower the oxygen levels because they're using up the oxygen while they are breaking down the algae. And so as our oxygen lowers, this may be called a dead zone depending on how low the oxygen gets. And so you can see eutrophication happen. You can tell kind of what stage it is, especially if it's that green slimy color of the water, then that's the algal bloom. But then after that happens and it's no longer green and slimy because the algae died, they may put up warnings about how you can't get into the water because the bacteria count is really high. You may have even noticed this on your summer vacations or your spring breaks while you're trying to, go swimming in the ocean, and there's different warning flags up about what kind of bacteria are there. And then finally, you'll probably end up seeing like some dead fish, some other organisms that are dying because the oxygen is low. Very good. So what can we do to combat that? Of course, we can address the fertilizer. So this takes you back to Unit 5 about agriculture. Preserving wetlands. Wetlands were also mentioned in this unit. It was heavy on the human impact on wetlands, but if we can preserve those wetlands, wetlands are basically nature's sewage treatment plants. And so if we can filter the pollutants out there before it gets into the rivers and the watershed, that would help. And then, of course, with the use of sewage treatment plants, that can actually will remove that organic material and those nutrients before it goes back out to our watershed. So like I said, eutrophication is going to be on your exam. So I would know that for sure. I would spend some time going over that. And that's why I want to make sure we go over it today. This is also associated with the oxygen sag curve and BOD. So if it says anything about BOD, then it's probably in relationship to a eutrophication question. BOD simply stands for the biological oxygen demand. And so you can see the levels. And so if the demand is very high, that means that there's going to be organic waste in there. If the demand is very low, that means you don't have to worry about the organic waste in there, as there's plenty of oxygen. So that means that they're not breaking down that. Then looking at your oxygen sag curve, if you haven't looked at one of these yet, let's make sure we go over this. So this is helping us try to figure out where that source of pollution is coming from. And so you can see that as the distance downstream from pollution increases, you can see what happens to the BOD. It starts to go down. And then this is the oxygen levels. So if the oxygen levels are low, then I know that my demand is high. I mean, that just kind of makes sense. If they're demanding it, then of course the oxygen is going to lower. And then as we move farther downstream from that nutrient source, then our oxygen levels will start to rebound and get high because the demand is low. And so you can kind of see this with the fish here, and you would apply that to what kind of organisms would be able to thrive in a low oxygen environment. Not very many. Most organisms are going to need that higher oxygen. And so that's why you're going to have those fish die-offs. And then like I mentioned too, the oceanic dead zones, and we talked about the Mississippi watershed, that it all goes to the ocean. And you can see worldwide that when these watersheds lead to the ocean and they're bringing all of the nutrients with them, that you can have the same eutrophication event happen on an oceanic level. And then you would have the same effects there. So it could be in a pond in your backyard, or it could be more large scale, like the ocean, where the oxygen becomes very low because of, it all goes back to the excess nutrients. But understanding that chain of events in the middle is very critical to understanding eutrophication. You got to remember that the algae blooms, then algae dies, then bacteria thrive, and then the bacteria are going to use up the oxygen, and that's when everything else is going to die. Okay, so sewage treatment was thrown into this unit, and I think that's because it goes very well in hand with a solution for eutrophication. Sewage treatment, I would know a little bit about each level, primary treatment, secondary treatment, tertiary, final steps. It's really all about breaking up the water from the actual physical material, and then treating the water and removing disinfecting it, removing the organic waste before it goes back out to our watersheds. Okay, so here's a diagram of what a wastewater treatment plant would look like, going through the steps. And again, just something to kind of look over. Okay, so for the sake of time, let's go through some sample multiple choice questions here about, this one's about dissolved oxygen and eutrophication, and then we'll see where we are for time. Okay, but let's try this one. So a point source discharges waste into a stream. Which of the following graphs best depicts the expected pattern for dissolving oxygen in the stream as a function of distance from a discharge point? So think back to what we talked about, that oxygen levels and where we're throwing in the pollutant. Okay, I see an E. You got to think where it's being discharged. That's where you're going to have that organic material that the algae is going to eat, but then going to die. And so you have to think, what's that going to do to your oxygen levels? And so yes, very good. So if you look at E, you can see that the oxygen is very low, and then the further you get downstream, then it starts to rebound again. So very good. So that looks just like that oxygen SAG curve that we just went over. Okay, here's a eutrophication question. So which one do you not want to do to deal with eutrophication? E again, very good. The last thing we want to do is add nitrates. That's what's got us there in the first place. Okay, here's when we got to look at some data and interpret the data before you can answer the question. And again, these are going to be very common on your exam. So I'll give you a minute or so to kind of digest all of this about this laboratory experiment showing dissolved oxygen in water. And there's 5 tanks, and you can see that in the 5 tanks, we are adding organic waste and looking at what it does to dissolved oxygen. So it's asking you, why would the dissolved oxygen after 1 week decrease? So what's happening in those tanks? C, very good. The algae multiplied, and then it died, and then it decomposed. So that's understanding that critical series of events in the middle between the release of the nutrient waste or the organic waste, and then how did we get to the low oxygen levels? Understanding those steps in between, the algae multiplying, then dying, then decomposing. Okay, sewage treatment plants. This is one way to address eutrophication and those biological pathogens that we learned about earlier. So which of the following is true? C again, very good. They are not designed to remove pharmaceutical chemicals from wastewater. So, when we were talking about like those endocrine disruptors, that may be one of the possibilities that's leading to the aquatic organisms affecting their reproductive success. Okay. So a lot of those things they cannot, because they weren't designed to take those out of the water. They were designed to remove the solids. They were designed to remove the nutrient waste. They were not designed to remove the pharmaceuticals. So very good. Okay, and one last one over wastewater treatment here. And very good. That's why they have drop-off days. So think about what's going to happen first. I think you're saying E. Yeah, so first you got to think about what happens first. You're going to have to remove the large debris. There's all kinds of things that are going to show up there. Everything from, what the Ninja Turtles had down in their sewer to organic waste. And then the very last thing you're going to do then is kill the pathogens with either chlorine or UV or ozone. And then if you can kind of fill in the middle in between, like that helps me figure out that that we have the P here and the Q there. So yes, then the second thing that happens would be the flocking agent. Very good. And then those particles are going to settle out. So if you said E, good job. Okay. So for the sake of time, I did have some more that we could have done together. However, for the sake of, and it's now 1:30, I'm going to go ahead and come back to you guys. And I'd rather kind of spend our last final minutes making sure you guys don't have any last minute questions or need anything. Instead of, because the multiple choice practice, there's lots of available resources out there for you to do along with FRQ. If you need help with anything, feel free to reach out to one of us, but I just want to see if there's any last minute questions or anything that you need help with before we go our separate ways. Yes, and then there's the link down there.
Thanks to everybody for showing up on a Saturday when it's beautiful outside, just to make sure you're ready for the exam. We appreciate your participation.
Okay, well, if you don't have any final questions, enjoy your weekend, be nice to mom tomorrow, and, good luck on your exam, everyone. Okay, see you guys.